Hello dear student, I am Monday. Today in this video we are going to discuss an important question from CSIRNET June 2021. Okay. So the question from June 2021. Okay. So there are four options given 1, 2, 3, 4. Okay. So we are going to be having one by one. Okay. So first of all, I am naming it V1. V1. Those matrices belongs to M such that x equal to x. Okay, this is a subset of M3. Okay, so it is subset of R or not. So first we take two vector and two matrix x and y from V1. Okay, and two scalar alpha beta belongs to real number. Since x y belongs to V1, from here we get x equal to x, right? And since y belongs to V1, so we get y equal to ya. This number one. Now x into alpha x, sorry, no, a into alpha x plus beta y. This will be a into alpha x plus b into beta y. Okay, so scalar it's a commute, so this gives x a into alpha into x. This is beta into by. You can write this like as alpha, and from here 1 you can write this x a, and beta you can write yb. Okay, now from here you can write easily alpha x plus beta y. This will be a, right? Beta always beta y. This will be a, right? A. This is a. So this will be beta outside. Beta will be outside. This is a. Okay. So beta will be outside. This will be a. Okay. So alpha x plus beta y. Now outside will be a. So I prove a into alpha x plus beta y equal to alpha x plus beta y into a. So this implies definition of V1 alpha x plus beta y will belongs to V1. Now x y are arbitrary, so you can choose, you can write x y for x belongs to V1 and for x alpha beta belongs to R. From here it is found that V1 is a subspace. It follows that V1 is a subspace. V1 is subspace of M3. Okay, so this is the option 1 is correct. Option 1 is correct. So in the question option 1 is correct. Now option 2. Option 2. I am naming V2. Those x belong to M such that x plus a equal to a plus x. Okay. Now clearly this zero factor belongs to this set, because zero matrix plus a, this gives a, you can write this a plus 0. Okay. It will imply the zero matrix, zero equals matrix. Zero matrix belongs to V2. So V2 will be non-empty. So it will be non-empty. Now if we choose two matrix, for all matrix xy belongs to V2 and for all scalar alpha beta belongs to R, we always have alpha x plus beta y plus a. This can be written as a into alpha x plus beta y, right? So this implies alpha x plus beta y, this belongs to V2. For all, we write for alpha beta belongs to R and for xy belongs to V2. So from here you can follow that V2 is a subspace. Subspace of M3R. Okay, so this implies option 2 is correct. Okay, this option 2 is also right. Now Going to option 3. Those x plus m such that trace of a is equal to 0. Option 3. V3. V3 is the those x plus m such that trace of ax will be 0. Okay, this is the given matrix. Now it is clearly subset of M3R. Okay, clearly subset of M3R. Now we will prove it is subspace of M3R. So first of all, check whether 0 vector belongs to this set or not. Now trace of if you choose x is 0, then a into 0 matrix will be a into 0 matrix will be 0. So trace of 0 matrix will be 0. Okay. So from here you can say 0 matrix and 0 3 cos 3. 0 matrix belongs to V3 and V3 is non-empty. Okay. Now choose two matrix. Let x and y be two matrix from V3 and two scalar alpha beta belongs to R. Then since x belongs to V3, from here you can write trace of ax will be 0 and here you can write trace of ay will be 0. Name it 1. Now for property of trace of a into alpha x plus beta y. This would imply trace of alpha x plus a into beta y. Okay. From here you can write alpha into trace x for trace of a alpha plus b beta equal to alpha trace a plus b trace beta. So this is the b trace ay. Right. Now trace x is 0. So from here you can write alpha into 0. From here you can write beta into 0. This gives 0. Okay. From by 1. So this implies trace of a into alpha x, b into beta y will be 0. Okay. So from the definition of V3, this implies alpha x plus beta y. This belongs to V3. Okay. Now x and y are arbitrary, so we can write this for all x belongs to V3 and for all alpha beta belongs to R. Okay. So this implies V3 is a subspace. So V3 is a subspace. This is subspace of M3R. Okay. So option 3 is also right. Option 3 is also correct. So this option 1, 2, 3 are right. Now option 4. Determine x equal to 0. Option 4. Option 4. Name it V4. I name it V4. V4 equal to those x belongs to this set such that determinant of ax will be 0. Now determinant property is not linear. Okay. This is subset of M3R, you can say. Now whether it is subspace of M3R or not. Now determinant property is not linear. Okay. Because you can never write determinant of a plus b will be equal to determinant not equal to determinant a plus determinant of b. Okay. Because if you choose the matrix, so I am choosing the matrix, a will be 1 0 0. Okay. And b will be this 0 0 1. Then this implies determinant a will be 0. Okay. Then determinant b is also 0. But if you made a plus b, this is 1 0 0 1. Okay. Then determinant will be determinant of a plus b. This will be 1. I know it is. It's not equal to determinant a plus determinant b. Because determinant a plus determinant b will be 0. Okay. So determinant property is not linear. Since it is not linear, so this is not subspace. Okay. So in this question, correct option are option A, B, C. Okay. So both option is incorrect. So in this question, correct option are A, B, C. This three option correct in this question. This question from June 2021. Okay. This question from part C. This is 4.7 mark. Okay. Now we are going to solve one more question from Tifr GS 2011. Okay. I am writing the question. Question 1. This question from Tifr GS 2011. Okay. This is a true-false question. Question of true-false question. What is the statement is a bounded function, a bounded continuous A bounded quantum function on R is uniformly UC, uniformly continuous or not. This question from true plus is it true or not? A bounded continuous function on R is uniformly, because it's saying that if suppose if a function from real to real, it's bounded also and also continuous also, then does the function is UC uniformness or not? Okay, verify true or false. So I am choosing the function this. If you choose the function fx equal to sin x square, this is real world function. Okay, this function domain is R and range is also R. Okay, domain is R and codomain is also R. If from R to R, f is equal to sin x square, then this function is clearly continuous. Okay, because the sin function are continuous on R. So this function is continuous on R. Okay, also it is bounded because mod of sin x square will be less equal to 1 for this square. Okay, so this function also, this implies f is bounded also. Okay, so f is bounded, f is continuous, but f is infinitenous, no, f is not infinitenous, because if you try to find f dash x, f dash will be cos x square, and this is 2x. Okay, for all x square. Okay, this is f dash x. This is not bounded. Its derivative is not bounded, because if you choose a sequence xn, let xn equal to 2n plus 1 root 2n plus 1 pi, which is sequence is this root is equal to root under 2n plus 1 pi. Okay, then this gives f dash root under 2n plus 1 pi cos root under 2n plus 1 pi, this is 2n plus 1 pi, and this gives 2 into root under 2n plus 1 pi. Okay, now cos 2n plus pi, this will be minus 1. Okay, this is minus 1, and this there is n. Okay, so ultimately it will be minus root under 2n plus 1 pi out of z2. So if you take limit n to infinity, this goes to infinity, this goes to infinity, n to infinity. So f dash is not bounded. This f dash x is not bounded. Okay, so since derivative is not bounded, this function derivative is not bounded, so this function can never be infinitenous. Okay, so this function is not continuous on R. Okay, so sin square function is continuous, bounded, but not infinitenous. So this statement is true. This is false. Okay, a bounded continuous function may not be infinitenous. This is false. Okay, a bounded function on R may not be infinitenous. Okay, the example is sin x square. The example is sin x square. Okay. Now I am writing one more question. This is also total question. Question 2. So saying let fx be a function and gx both are infinitenous. You see infinitenous on R. Okay, then does it imply product fx and gx is also infinitenous on R? Okay, this is true for question. Okay, this question is true for type, and it is question from Tifr GS 2018. Okay, this question from part B. Okay, so this question is false. Okay, you can take example. Let I am taking fx equal to x and gx is also x. Okay, the identity function. We all know identity function is infinitenous. Okay, we all know this function, then f and g are both infinitenous. On R. Okay, now if you compute a pointers product f into g, this gives x into x. This is x square for x belongs to R. Now this function is not infinitenous. F dot g is not infinitely only continuous on R. Okay, because if you name it the function, let hx equal to fx dot gx, then it's x square for x belongs to R. Okay, then its derivative will be this polynomial function, so its derivative is 2x. This is not bounded, this tend to infinity, is x tend to infinity. Okay, not bounded. So when derivative not bounded, so H never be inhomogeneous. So H equal to F dot G is not inhomogeneous, not UC. So F and G are both inhomogeneous, but their product is not inhomogeneous. Okay, so product of two inhomogeneous function may not be inhomogeneous, but composition of two inhomogeneous function, if suppose F is inhomogeneous function, but this is true. Suppose if F G are both inhomogeneous on R, okay, then their composition F composite is inhomogeneous. Okay, this is valid statement, but the product composition is not same like product. Okay, composition is different from product. So composition is inhomogeneous, but the product is not inhomogeneous. Okay, so I have discussed in this video one question from CSIRNET and two questions from Tifr. Okay, in the upcoming video we will discuss more question from CSIRNET, Tifr, NVSM, GATE. Okay, so please follow my channel and subscribe my channel. So thank you.